Professor Kostas Skenderis, and it's a pleasure to introduce him now. So before I do the formal introduction with his list of accomplishments and stuff like that, I thought I'll say something more informal, which is that his work has been influential on many of us, especially some of the graduate students sitting in the audience. His work on holographic renormalization has been pretty much the key to compute stuff in what is known as the holographic duality. And it's used almost on a day-to-day basis by researchers across the world. Secondly, he wrote a nice set of lecture notes on the same topic, which I think most of the students in the audience are. He became an assistant professor at Princeton in 2001. From 2003 to 2012, he was an associate professor and then a professor at the University of Amsterdam. In 2012, he's moved to the University of Southampton, and he's launched the Southampton Theory Astronomy, received multiple awards. He's received the VICI award from the Netherlands Organization for Scientific Research. He's also the editor-in-chief of the prestigious European physics journal C, which many of us publish in. Some of his research interests include general relativity, cosmology, quantum field theory, and string theory. He's worked extensively on the holographic principle, and his work has been influential, as I just mentioned in the beginning. He'll tell us about what the holographic principle is. And as I said, he's a great communicator and a big figure in the field. So especially the students in the audience should not hesitate to ask. Maybe you can start the talk.
Okay. Yeah, thank you very much for this nice introduction. I would like also to thank the organizers for giving the opportunity to give this talk. It's been more than a year. We started collaboration with the group here in Chennai, and it has been wonderful. We already had one conference in Southampton, and this is the second one, and it's very inspiring. And I hope today to explain a little bit about science. So I have a rather exotic title, the holographic universe. And the words themselves mean different things to different people. So what I would like my aim today is to, at least by the end of the talk, to get some idea of what these words really mean in science, in science. And I also like to convey the scientific process, what it means to do science, and what it means to try to think about the universe. So I'd like to start this colloquium with a few general remarks. So we interact with our environment, and many of the things we do and the way we think about the world is about how we perceive things from everyday reality. And science itself was born out of the desire to understand the world around us. But what we learn over the course of the history is what we perceive as physical reality may not accurately reflect the workings of nature. So during 3/4 of this talk, I will go through a little bit about how things evolved and how the ideas moved from one paradigm about physical reality to another. But first, I'd like to underline a little bit about this because it is a little bit stunning if you think about it. So every day we see the sun rise through the sky, and for thousands of years, people thought that the universe is something like this, where the Earth was in the center and everything else was moving around. Of course, we now know this is not the case. And thinking back, you can say, how could they think, or why they couldn't think better? But it's very easy to fool yourself. So this I took from the internet. So here I have a checkerboard, or it looks like a checkerboard, with a little cylinder in it. So it looks like it's 5 times 5, where half of the squares are white and half are black, right? Anyone thinks that this is not a checkerboard? So and at least when I look at it, I think this is black and this is white. Yeah, that's how it looks like. So now let's actually look what it is. So we're going to do, in a sense, an experiment, what scientists would do. So what are you going to do to check it? So you need to bring this close to that. So we're going to come here and cut it. And then moving close to the other one. So that's one way to do an experiment, to see is this true or not. And when you do this, you see actually B is exactly the same as A. So this checkerboard is not a checkerboard because there's 3 different shades. So why do we think it's different? And the way we think it's different is because we have this cylinder here. And our everyday perception, our brain is wired so that we accommodate for the shadow that is going to come from the cylinder. It makes us think that what we see here is what we expect. So we have an expectation based on our perception, and this can fool us. Now, when it goes to the actual science, sometimes we have to probe scales, either small or very big, which are very different from our everyday perception. And that's why our physical theories are not necessarily the same with what you would think based on everyday perception. So another example I want to make, and we're going to come back to that, is that sometimes some objects may look very different depending from which perspective you're taking. So if you look at this object, if you look at it this way, this is the duck, this is the mouth of the back of the duck, and this are the wings. If you look at it this way, this is more like a rabbit. This is the face of the rabbit, and these are the legs of the rabbit. So it's the same object, and it looks very different depending from where you look at it. And if it actually happens in nature, this means you can learn a lot of things about this object that you couldn't think they're possible. Like if you look at it this way, you know it's a duck, so it can swim in a pond. If you look at it that way, you know the same object can run very fast. And you wouldn't think a duck can run very fast. But if it is both a duck and a rabbit, it can do both things. And this is an example of what we call in science duality. So it's the same object has a dual meaning. And a big part of the advance in science the last 20 to 30 years comes from trying to use this type of ideas about dualities, try to understand one object, view it in a different way. Okay, so that's a little bit generalities about perception and scientific theories. Now let's go back to scientific theories. I think the oldest theory, which is probably can be called a scientific theory for the universe, is due to Aristotle, about 2,500 years ago. So his theory was that everything is composed out of 4 different elements: the air, water, earth, and fire. And depending on the composition, then the motion of the objects was determined by its composition. So if something is mostly made out of earth, like if this is made out of earth, so if I drop it, it's going to go down. It's going to go down because it wants to go towards the element that makes it. Okay, it looks like a reasonable theory because most of the things, like if you have a smoke, it goes up because it looks like it's made out of air. And it looked so reasonable that it sort of dominated what one might call science for about 1,600 years. It's perhaps the most successful theory of all time. No other theory survived for so long. But then, of course, we now again know that's not how things work. And I think where modern science started, it started with kind of Galileo and Newton. So the Newtonian universe, this is the thing that it's most according to our nowadays experience of the world. So Newton started by setting the stage. He said we have space, and that's in his own words. And space is absolute, and it does not depend with anything external. It always remains there, and it's immovable. So it's something like this. So it's like space is there, and everything when it moves, moves relative to this absolute space. And then he wanted to understand how things move, what are the laws of nature, how the planets move, and so on. So you need to understand what happens when time passes. So we need to define also what time is. So again, in his words, time is absolute true mathematical time, and from its own nature flows equally without regard to anything external. Okay? And then, so now we have to set the stage. We have space, and we know what time is. And then he set out his theory for the Newtonian laws of physics. Oh, I think I'm missing a slide. No, this is going to come later. But of course, we now know, again, move forward about 300-400 years. We know that time is related to space. So time is like a fourth dimension. So we have space and time are not separate. They are one entity. There is a space-time. So let's try to understand a little bit what it means when we say a space-time continuum. So suppose you have a box and you have two molecules inside the box, the green and the red, and they move around. So now to understand the space-time continuum, what you do is we take snapshots of this, and then we draw the position of the particle here. So we put a new axis. And every time the particle is at some point, we draw it here, and same for the red. So now we have a space-time, so space and time, it's one entity, space-time, and everything moves along to the world line. So that's what space-time is. Now going back to Newton, now Newton set the stage with space and time, and he also formulated how things move, the laws of physics. So the objects move because we put some force on it. This is also something that the way we normally think also in everyday life. You want to move a box, you put some force and it moves. And also in Newtonian physics, if we know where this box is now, and we know what force we put on it, we would know exactly where it's going to be 5 seconds later. So you just solve the equations that Newton wrote, and then you find where it is. So this is called classical determinism, because at any given time, we can know exactly where objects are and how fast they move. Okay, but this notion of a force is, again, move forward 300-400 years. We now understand that there's some deeper thing behind it. So the reason massive objects move are not really because of some external force. They really move because of the geometry of space-time. So in kind of a slogan, Einstein's theory of gravity is that the gravity is equal to geometry. So if you have an object that changes the geometry of space-time, and other objects moves around it because the geometry has been curved. So force is not the real concept. It is, again, is a derived concept. Things move because of curvature, not because there is something external that acts on it. So this is a highly successful theory. It has been tested. Of course, if we think about the way things move around us, they move around the way Newton's law are describing, but they equally move around the same way as Einstein's theory would describe. But when you move to longer distances, then Newtonian physics stops to be accurate, and then you need to use Einstein relativity. So Einstein relativity accurately describes how satellites move around the Earth. They also accurately describe how the planets move around the sun. So that's distances of about 10 to the 9 kilometers. And it even accurately describes how the whole galaxy, how the stars move within the galaxy, and how the galaxies move in the bigger cosmos. And general relativity, for the first time, allow us to formulate the laws of physics for the entire universe, not just for the planets around us. We understand the history of our universe. We know that the universe, this macroscopic universe, the way we understand space and time today, is about 14 billion years old. And we can understand all of this evolution, how it started, how the galaxies formed, and we are out here observing the universe. But Einstein's theory itself has its own limitations. So we discussed earlier that time is another dimension, so we have space and time. So if we move backwards in time towards time 0, then the universe becomes more and more compressed in a small space, and it reaches a point where the equations that Einstein wrote stop to make sense. The theory does not make sense. So this is called a singularity, and we're going to come back to this singularity later on. So to understand the singularity, we need to understand the physics of the small. So far, I started by describing the physics of the distances we perceive. This is Newtonian physics. And then the physics of the big. This is general relativity. So now let's go to the physics of the small. So the physics of the small is quantum mechanics. So we all know what happens if you try to move an iron skillet. But if we now zoom in and I try to understand the structure of the material, this is made out of iron atoms, which is about 10 to the minus 8 centimeters. And then the usual intuition stops to make sense now. If you move further in, you go to the nucleus. So now the nucleus itself is, again, even smaller, 10 to the minus 12 centimeters. And if you further zoom in, then you have the nucleus have protons and neutrons themselves, again, 1 order of magnitude smaller. And if you further zoom in, then you find that this is also composed out of more exotic particles, which are called quarks and gluons. So quantum mechanics is able to describe all of these phenomena, all of these different small scales. It describes how electricity works, and it describes how the magnets work, electromagnetism. It also describes other forces, which are very short distance forces. It describes how radioactivity works, how our sun generates the energy, and describes nuclear physics. It's a very successful theory. It's perhaps the most successful theory we ever had. It agrees with experiment to unprecedented accuracy. So, but quantum mechanics that describes all of this phenomena, it has also, it's very counterintuitive when you actually see how the laws of physics are formulated. So in quantum mechanics, some questions cannot be answered with certainty. There are some questions which are not answerable. And previously, I described classical determinism. If we know the position of an object now and how quickly it is moving, suppose you are in your car and you drive with 30 kilometers per hour, you know that in 30 minutes, you're going to be 130 kilometers far from where you are. But in quantum mechanics, that's not possible. According to quantum mechanics, we cannot know with arbitrary well the position and the velocity of the object. So quantum mechanics formulates the laws of physics in terms of probabilities. So instead of having a classical determinism, this is replaced by determined probabilities. So the laws of physics describe the probability for something to happen rather than how this is going to happen. So these two different theories, the quantum mechanics and general relativity, make what we now call modern physics. These are the two pillars of the 20th century. These are the great advances, and all of this led to I mean, everything that the way we live today, you know, the fact that we have electricity, we have energy, we have GPS, all of this is based on these developments that happened over the last 100 years. But things are not, all is not good, even though we have been so successful, because Einstein's theory of relativity is not a quantum theory. And this is a problem because our world has both, and you cannot have one without the other. You cannot have both a classical description together with a quantum, because the quantum laws of physics are probabilistic, where the classical laws of physics are deterministic. So for consistency, you have, if one is quantum, the other has to be quantum as well. So how do we go about, so for over, I would say, 50, or maybe now 100 years, people have tried to solve this problem, how to quantize gravity, how to have a theory which is consistent with general relativity and is quantum mechanical. And there are many, many problems, so it's not an easy problem. So how do we go about tackling this issue? And here is another remarkable object that comes to rescue, black holes. Black holes are one of the most fascinating objects that general relativity predicted, and we have now actually observed. So there are objects that they have so strong gravity that everything that falls in cannot go out. So even light, when it falls in, cannot escape. So they have, so there is a so-called event horizon that if you pass that point, then you go into an area where you cannot escape and follow down and go to a place which is again a singularity. So you remember earlier when I discussed the universe, I said that as we go back in time, we reach a singularity where the actual equations do not make sense. So something similar happens inside black holes. So we know they're there, and we know that as you go back in, you reach this singularity. So to understand the meaning of that singularity, we need quantum mechanics and to need to understand how to treat black holes quantum mechanically. And this is something that some progress was made already about 50 years ago, before we move that. So black holes are also very unique. So black holes can form when stars are collapsing. If you have a very massive star and it collapses, then it forms a black hole. And no matter what are the properties of that star, it could be, a star that had a civilization in it, or it could be a small star with some property or another. All of them, they're going to end up being described by the same solution of Einstein equations. And in the words of Chandrasekhar, whose name this colloquium is named, black holes are the most perfect macroscopic objects, because the only thing that you need to understand them, the only concepts that you need is space and time. But once you have them, you also have the problem that once you go inside the black hole, you find the singularity. So you need to try to understand how to deal with it. And Bekenstein that we'll describe in a moment. So I said a few minutes ago that classically nothing can escape from a black hole. If you fall in, you fall in. You can never go out. Not even light can escape. But quantum mechanically, black holes are more like burning coal. They have a temperature and they have an entropy. So what is an entropy? So an entropy is a measure of the different ways, different specific ways in which a specific system can be built. And in the normal matter, like a piece of wood, the entropy is proportional to how big it is, because if you have a bigger object, there are many different ways to build it. If it's a smaller object, there would be fewer ways to build it. So normal entropy behaves like like the volume it occupies. But then Bekenstein, in the beginning of the 70s, discovered that for black holes, something very strange happens. Instead of their entropy being proportional to the volume they occupied, they're actually proportional to the area of the horizon. And that's the famous formula. The entropy is proportional to the area, and the others are constants. So this means, so we described earlier that early entropy means how many different ways you can make an object. What are the degrees of freedom that make the object? So the black hole is like putting zeros and ones. So if you have, let's say, 1 degree of freedom or 0 degrees of freedom on each kind of on its surface, so then the number of degrees of freedom that make up the black hole are proportional to the area rather than the horizon. And this is very surprising because all other matter systems, all normal matter, has an entropy that grows like the volume. So this now led to the so-called holographic principle, which was formulated by Gerald Taft, which has got the Nobel Prize in physics in 1998, I believe, and Lenny Susskind. And then they suggested that there is a reformulation of gravitational theory in terms of another theory that describes the dynamics at the boundary. So why is it called holographic? So let's first briefly review what are normal holograms. So normal holograms are optical holograms. So in optics, holography is a specific technique that allow us to encode three-dimensional images in a two-dimensional surface. So like in an example is a hologram we have in credit cards. So if you shine light in credit card, it looks like the bird is flying. So you have a three-dimensional image which is encoded in a two-dimensional surface. So similarly, in the idea of holography is that the entire universe is like a hologram. So the entire information about the entire universe can be encoded into a theory that lives in the bounding sphere of the universe. And that's a postulate. Again, with physical theories, what we do is we look at the problem, we make a postulate, and then we test it. And the postulate is that the underlying description of the universe is in terms of some three-dimensional quantum theory, which is very similar to the theories that describe electromagnetism and the nuclear forces. So here, three-dimensional means two space and one time. So this is like, going back to the optical illusion I had at the beginning. It's like asking, this is our universe. This is a three-dimensional quantum theory, and a priori they look very different. So they look like nothing, like the exact opposite of one another. So this has more dimensions, it has gravity. This doesn't have gravity, has one dimension less. But nevertheless, this postulate says these are meant to be the same. And as a scientist, our task is what I did in the very beginning, try to kind of cut this open and move it over and see whether this idea makes sense. If it doesn't make sense, then you try to solve the problem. You go back to the boarding, you're going back to the beginning and try to solve the problem again. So to understand this, okay, we need at least a simpler model where we can, again, physics works with models. So you have an idea, and then you try to formulate it in simple terms so that you can test it. So you can have a proof of concept. So a concrete realization of this idea was obtained a few years later. So the principle was formulated in the beginning of the 90s, and then a few years later, Juan Maldacena made the kind of famous by now conjecture, the so-called ADS-CFT correspondence. And since then, this has been a topic that dominated high-energy theoretical physics research. There are about 18,000 research papers that were written on this topic today. So I'm going to give a few words about string theory, because this congruity realization came through string theory. So the idea behind string theory is that the fundamental objects are not point particles, but they are little strings. And then you can get different particles depending on how the string is moving. So it's like if you have a guitar, depending on how you hit the chord, you get a different note. So similarly here, depending on how the string vibrates, you get a different particle. And the string itself is very, very small. I mean, I showed you earlier the size of the object. So the string is about 10 to minus 33 centimeters. So things are composed out of strings, not point particles. But once you have strings, string theory has also objects where the strings can end. This is called branes. So string theory is a theory of strings 30 years ago. And using this ingredient, different ways to make a black hole, by using these objects, these branes, these are called D-branes. D-branes with strings. And then once one has understood, at least in special cases, how the black holes behave, one was able to make a concrete realization about how holography would work. So even now, we are now 25 years later. I think we're only just beginning to understand holography and what are really the rules of the game. What is the holographic dictionary? This is actually my area of expertise, this holographic normalization mentioned earlier. Comes into try to understand how do you build this dictionary. And if holography is true, this means there should be a way to make the holographic nature of the laws of physics manifest. And as with many other important developments in physics, this usually requires new mathematics. And this has also been the case here. So this development in physics about holography has also led to kind of new mathematics, which is, again, an evolving and developing field. But what does it actually mean about physical reality? At the face of it, this suggests a dramatically different picture of what physical reality is. Because we traded gravity and one dimension. So gravity is something we feel every day. So when we get up, we feel gravity. We're able to walk using gravity. And we also clearly see 3 dimensions. I can move forward, sideways, or I can jump up and down. But nevertheless, if this idea is correct, it says that gravity itself and one of the dimensions is an emerging phenomenon. So what does it mean to have an emerging phenomenon? So let's briefly discuss that. So emergent means that this is not part of the fundamental laws, but rather appears as a consequence of dynamics. And here I try to illustrate this with an example of a temperature. I think most people in the room would be familiar with the concept of a temperature, would be less familiar with, perhaps, with the motion inside the box. So suppose you have a large number of particles inside the box, and they all move around. And you want to describe them. Okay, so one simple way to describe them is to go to each and every one and say what it is and how fast it moves. Like here, they're going to be, I don't know, maybe there are about 50 molecules in there, and they all move. Now, if you let them move for long enough, then eventually the average velocity with which they move is going to be roughly the same. They're all going to move with the same velocity, because if one moves very fast and hits a slow one, then the slow one would start moving faster. And if you wait long enough and then they interact long enough, then they will equilibrate and they're going to have the same average velocity. And the same average velocity, then we call temperature. So temperature is not a property of any of the molecule on its own, but it's a property of a collection of molecules that move around and have been interacted enough so that their average velocity is the same. So even though the most accurate description would be to tell you the position and velocity of every of these molecules, in practice, this will not be a very useful description, because I will need to give you a lot of numbers. Where if the system is in equilibrium, there is a more useful description in terms of an emerging concept, which is temperature. That's why in the radio, they say tomorrow is going to be 30 degrees, so telling you how each molecule is moving in the air and what is the predicted position and velocity the day after. So holography is gravity, and one of the dimensions, according to the holographic principle, is kind of similar. So bringing back kind of the same graphic that I showed you earlier to demonstrate space-time, but now reinterpreted in a slightly different way. So now we have a system in 3 dimensions, and we view the system at different energy scales. So as the energy scale changes, the way the system behaves changes as well. And then for every energy scale, we again record an additional dimension. And then altogether makes makes the hologram. So the hologram is, it says, the 3-dimensional space, and then the imagined dimension is this energy of the system. Okay, so what can we actually learn from this? Suppose it's true. Okay, well, what have we done with it? Well, first of all, I started describing the problem with Einstein's theory. So if you go back in time, you reach the point where you have the singularity. What actually happened there? Is there a beginning of time and space? Does it make sense to ask what were the laws of physics before the Big Bang? I actually get a lot of this question when I go and give talks at schools, and you say there is a Big Bang. What about before that? That's it is a sensible question, but can you make it a scientific question? And what were the laws of physics before time and space, the way we perceive them today, existed? So this type of questions, I would say, the questions you could discuss over coffee, but they were not scientific questions before holography was put on the table. Now this start to be scientific questions. As it was mentioned in the introduction, there is a holographic framework for cosmology, and you can start addressing these questions, and you can even start comparing with data. So I'm not going to go through the details of that, but that's in concrete advance. You can start to make scientific questions out of questions that humanity was pondering for thousands of years. Why are we here? What's the time? Why time? Why space? Holography is an example of a duality. So from one, if you view the object in, let's say, this way, this is the universe the way we perceive it. If you use the other way, it's, the actual description is in terms of a theory in one dimension less. And this is very useful because, as I said earlier, there are some properties of a system you can't quite understand if you look at it only in one way. You can only understand them if you view it the other way. And this is a way that people try to use these holographic dualities over the last 20 years, and there has been a lot of successes. So one can also try to use gravity in order to answer quantum questions. So here we'll try to use quantum theory to understand space-time. But when you have a duality, it goes both ways. You can try to understand quantum systems by asking questions about gravity, and sometimes it's easier to answer the question in terms of gravity. And here I just put two applications. There are many more. So I described earlier that as you go deeper and deeper into the structure of matter, there is a point where you have quarks and gluons. Now, most people will not have heard about quarks and gluons because in normal matter, you cannot see them as free particles. But when you hit the system, they make the system, you put a lot of energy into the system, this liberates the quarks and the gluons, and you get a so-called quark-gluon plasma. And people have tried to understand the physics of that system for a long time. And it was only through, and this is the use of the methods using these holographic dualities, that we start to get a better handle into this question. Another question, which is perhaps even more, let's say, important for our planet, is, let's say, high-TC superconductors. So there's clearly an energy crisis. And we generate energy, but lots of energy we lose a lot of energy by transporting it from point A to point B. And it would be great if we can find a way to transport energy without losing any of it in the process. And if you cool the system at very low temperatures, there is a way to do that. These are called superconductors. But of course, to cool the system to very low temperatures requires a lot of energy itself. So that cannot help us solving the energy crisis in our planet. So if we would only manage to find a way to engineer superconductors at high energies, high meaning at temperatures comparable to the ones where we live, then this would have essentially solved the energy crisis in the planet. And there has been a lot of work going into this from people studying materials, and it is a difficult problem. And this is another topic where you have now a new tool to try to understand what is the physics of these high-TC superconductors, which is certainly not there, but gives you a new tools to study problems that could also benefit humanity more generally, kind of more technologically driven issues. Now, another topic that I haven't covered is about the relation between quantum information and holography, and that would probably require another colloquium to discuss. There are very deep connections between black holes and quantum computers. One can view black holes as a system which maximizes information storage. So in a sense, when an astronaut kind of falls into a black hole, and dissolves into and falls inside, the information about that astronaut is converted into an information which is stored into the black hole. And lots of interesting recent works exploring this connection between quantum information and holography. That's a new emerging field that happened in the last 5 to 10 years. But that's for another day. So I'm just going to finish now by just putting this slide. So the 20th century was the century of general relativity and quantum mechanics. This led to an enormous technological advancement and also a new paradigm shift about what physical reality is. Will the 21st century be the century of holography, where we see similar revolutions, will again change the way we understand physical reality and also lead to a lot of new technology and new knowledge? Thank you.
Yeah, we can take questions now, but can I have a mic or something? Okay, if there are any questions, you can raise your hands.
Emergent phenomena using holography principle?
So in this holographic picture, so you have a three-dimensional theory that has no gravity, has only forces like electromagnetism and nuclear forces, this type of forces. And then when these interactions become very strong, then, like in the example of the temperature, when the system interacted enough and then you got the emergent phenomenon, then the picture is then when the interactions become very strong, then gravity emerges together with the additional dimension. So the additional dimension is always there in the system as the energy of the system, but it's not perceived like a macroscopic dimension on equal footing with the other two.
How quantum gravity and singularities are related?
Okay, so when you move to very small distances, then you need to use quantum mechanics. But then the singularity was a property of the system that included gravity. So to understand singularities, to understand what are the laws of physics, you need a new theory. And this new theory should be such that it describes both the small and it also describes gravity. So it is a quantum theory of gravity. So then if you have the right quantum theory of gravity, so that theory should have the explanation of what are the laws of physics at the singularity. And then we started saying that Einstein's theory of gravity is not a good theory because of the cosmological singularity. And then we move on to kind of black holes, and we found again a singularity. And then the black holes gave us a hint of what reformulation we might look for. There's still a lot of work to understand this black hole singularity using the idea of holography. This is a very during the last few days. But then once you understood this, then the next step would be to kind of move to cosmology to formulate the cosmological evolution holographically. And then that would allow you to resolve the initial singularity and answer the question, was it a beginning, or what are the laws of physics there?
Sir, is the black hole singularity similar to AI singularity, information singularity? Whether any connection between artificial intelligence singularity and black hole singularity?
Artificial intelligence and black holes?
Some futurists say there could be a artificial intelligence singularity in the future, the near future. Is it similar to the black hole singularity?
Artificial intelligence singularity, is this?
Is similar to black hole singularity?
I don't know what is an artificial intelligence singularity, though.
But Stephen Hawking, persons like him, says that the very moment AI outsmart humans, there would be a singularity. There will emergent singularity.
Yeah, I think in a sense this was more Stephen Hawking's way to be a little bit provocative for the public. So I don't think that is. This is just try to be provocative about artificial intelligence, and we have to think seriously about it, not let it move on its own. We have to think about the consequences of developing artificial intelligence.
Okay,
but
so
there's no connection between a possible singularity due to artificial intelligence and the black hole singularities I discussed there.
Sir, my second question is regarding the emergent behavior of molecules' temperature. How the erratic climate is connected with it?
The climate change is, I think in a sense, the underlying physics behind it is understood physics. It is, you have a system which is driven out of equilibrium because we disturbed it. So I had this little box with the particles moving, and I said, if you wait long enough, everything is going to be in equilibrium. Now suppose suddenly you disturb the system. Then when you disturb the system, of course, the system is going to start to moving in different ways before you reach a new equilibrium again. And humanity has done some disturbance into the system. And that's one of the reasons that we see this change in the weather.
Evening, Prof. I have like two questions. One is more like of a view. So what's your view on inflation theory? And the second one is, can we use holography to get rid of exotic matter for Alcubierre drives?
Let's first answer the first. I didn't understand the second, but let me answer the first question first. So inflation is an effective theory. So it's not a fundamental theory on equal footing with what we're discussing here. One can view inflation as an example of a holographic theory, and there can be other models which are holographic. So inflation may or may not have happened. It's one possibility for the very early universe. But even if it happened, you still need to understand what happened earlier in time, and that's where, again, holography comes in. Second question?
It was, for Alcubierre drives, we need exotic matter. So can we get rid of that somehow using holography? I don't know if that's the right phrase to use.
Now, the matter in our universe is what it is. In a sense, the laws of physics are there to explain how things are working, not why they are the way they are. So if it is, for instance, we don't understand, I haven't touched this at all in this talk, but we don't understand at all, what is dark matter. So, in a sense, observations suggest, especially with cosmology, that there is an exotic form of matter called dark matter, which is out there in the universe, but we don't understand what it is. So holography could be a tool to kind of try to model or find a way to understand what it is, but you're not going to get rid of observed phenomena. You might have a different explanation for them.
Hi, sir. So my question is regarding black hole entropy. So what happens to that entropy when a black hole evaporates? Does it simply get vanish, or cause
No, the entropy doesn't vanish. So we have a second law of thermodynamics which holds. So the entropy always increases. So it's going to go back in the universe. The big question with a black hole when it evaporates is what happens to all the information which is stored inside it. And this is a very active debate still in the community. Try to understand what happened to that information. I mean, the belief of the community is that the information goes out into the system, and there are some models that say how that happens, but it's still a topic which is debated. I mean, we had actually the last talk in this conference was about that.
So, like, can that information be retrieved, or like it just gets lost in the universe?
No, the information, there was a lot of debate, back in the 80s and 90s, can information be lost? If information is getting lost, this means we have to replace quantum mechanics. Because if quantum mechanics is right, information would never be able to be lost. You have to change the loss of quantum mechanics. I think the community believes now that quantum mechanics is correct, and general relativity is modified, and modified according to the rules of holography. What is not yet completely clear is what is the exact mechanism for this information to go back to the universe.
So yeah, does holography explain how this happens?
Well, there are models that there are models and debate. There are different models, and different people debate. There is no definite answer. That's, I guess, another thing I want to say, since we're discussing a little bit about general in science. So science, the way science moves is first debate a topic, and then different models are put forward. And then when you have observations, you go and check which one agrees with observations. If you don't have observations, you make so-called Gedanken experiments, theoretical experiments, where you try to test the ideas with mathematics. And then once something is established, then you move forward to the next step. So I think with the issue of information loss, we are at the stage where we have moved since the kind of 80s and 90s, in the sense that we start to have concrete models about what can happen. So it becomes a real scientific question that fully can be answered in a way that all scientists agree. But we're not there yet, and it is a topic which is still debated.
Okay, thank you, sir. Thank you for the talk.
Sir, so how is the string theory related to the multiverse or the parallel universe?
Okay, so the multiverse, so string theory, if you try to understand what type of universes it predicts, some versions, there are some indications that there may be many different universes you can produce using string theory. And you would call all of this universe you could produce a multiverse. I don't think it's an established fact, even within string theory, that multiverse exists and it's out there. It's another topic which is kind of debated. So there are indications, computations, and again, in science, you try to, when you cannot understand the problem head on, you try to build toy models and simplify, make assumptions and approximations. And sometimes the conclusions that you would get might depend very strongly on the assumptions and the approximations that you have done. And then other people may analyze the problem in a slightly different way and reach a different conclusion. So this is still a topic of debate.
Hello, sir. Whether time originated after Big Bang?
Say it again.
Sir, whether the time originated after the Big Bang?
Okay, so I mean, again, what happens before the Big Bang? So there are theories that says that there is a kind of a three-dimensional theory which exists forever. And then when that theory becomes strongly interacting, then macroscopic time emerges. So from our perspective, there is before. There's a timeless theory before that, which exists forever, where the laws of physics make sense. You can describe what is going to happen. And then at some point, interactions become very strong. And that's at the point where a macroscopic time direction emerges, and then a view of gravity, the way we perceive them today. And then after that, we have 14 billion years, and we are today. So there is a theory which has all of these elements. But that's another topic which is, it's a topic of debate. It's not the ultimate theory. That's, at the same time, that's a topic where we have observational data from the so-called cosmic microwave background or the distribution of the galaxies. So when you write down a theory for the very early universe, then you can work out what are the consequences. So we know that after the Big Bang, there is an afterglow that left a radiation that goes all the way back to the period. Actually, if I go back. Yeah, so there's a radiation that comes from this period here. This is about 400 years after what we would call time zero. And then there is a radiation that comes from here and is observed by satellites. Actually, this graphic here was made by the WMAP team, and there is a newer observations by the European agency, the Black Satellite. And they observe this radiation. Actually, what they observe is something like what is put here. Then you can work out mathematically. You can see here it looks like green spots and yellow and blue. This is a code for temperature fluctuations. So some spots are colder than others, and you can work out mathematically what distribution of blue and green you expect, and then you can compare with what you see. And if your theory agrees, then that's a positive for the theory. That, in a sense, validates the theory. If the theory disagrees, then it's not a good theory. So I was asked earlier about inflation. So inflation gives predictions which are in excellent agreement with what you see over there. And these holographic models, they're also in excellent agreement with what you see over there. So we need more data. That's why it's a hot topic. Now, another new data that we're going to have in the next 5 to 10 years is the distributions of the galaxies. So the way that, so these little anisotropies, I start to lose the pointer. So this little green and blue dots, these different anisotropies, is what led to the galaxies later on. These are the seeds for formation of matter. So when you have gravity, it tends to club objects together. So if you have something which is denser than another part, it's going to start to clump together. And that's what generated the galaxies later on. And this has been involved with Einstein equations. So we hear and observe the distributions of galaxies. So the distributions of galaxies in the cosmos has incited information about what happened at the very beginning of the universe. You like to use that to test your theories for the very early universe. If your theory gives something that agrees, then again, that's a positive thing. If it disagrees, it's a wrong theory. Then you put it in the dustbin and you start all over again.
You said holography is projection of three-dimensional object on a two-dimensional surface. Then you said already...
No. I said optical
yeah.
Optical holograms. We have a two-dimensional surface, and then you can encode a three-dimensional image.
Then you said time is the fourth dimension. There are theories that the universe might contain multiple dimensions. How do you reconcile that?
Yeah, so it does look strange that we go up and down in dimensions, like string theory needs 10 dimensions. But holography would say we have a three-dimensional theory. Now, in string theory, some of the extra dimensions are very small, and the reasons we don't see them today is because they're very small. Now, in holography, you can describe this kind of 10-dimensional theory using a 3-dimensional theory where you describe not only the macroscopic dimensions, but also the small compact dimensions. So even though it looks, you go up and down all the time, there is a way to consistently include all elements into one framework.
Hello. Very interesting subject and fascinating talk. Thank you, Professor. I'm from, I'm probably the dinosaur here. So I graduated 50 years ago, and we didn't learn quantum mechanics also at that time. But my interest in the subject came from a different point of view after reading Michael Talbot's book. And it's not science, but the whole idea of a different look at reality, and there are a lot of common terminology.
It has the same title, has the same words, holographic universe.
Yes, yes.
But it's very different.
Oh, yeah, I
Yes.
know. So my question is, in terms of where is this leading? In the sense that, let's say, in 20 years, 50 years, do you expect, or is the expectation that there will be a more unified theory of everything like Einstein?
Yeah, my own expectation is like, if we view back, physics in the late 19th century, where in a sense we're at the high of the classical physics. Towards at the end, actually, there is a famous conference just at the turn of the century where I forget now who was. Someone declared the end of physics because we understand all issues except for two small problems. And one of the two small problems had to do with irradiation for black bodies. And this was what led to quantum mechanics. And of course, it's like opening Pandora's box and then completely change the way we view the cosmos. And then General Relativity followed a few years later. And through the 100 years, we now, at least the scientists, are at ease with quantum mechanics and general relativity. Still, this hasn't, I think, permeated completely to the general public, but the scientists are completely at ease with general relativity. Now, with holography, we move to a new shift paradigm about physical reality. And my own expectation is that this is the future. So if we move 20, 30 years from now, the laws of physics would have been reformulated in a way that make manifest that the laws of physics are holographic, rather than finding them in a roundabout way, the way we do now.
There seems to be some convergence, at a distant point in time, in terms of is there physical reality? That's the question.
There is physical reality, yes, there is. I think you are as real as you seem that you are.
Thank you.
Latest map of the cosmic background is given by the Planck satellite.
Yes.
So would it help to validate theories more by sending another satellite which has, suppose, a higher resolution?
I think with the Planck, we probably reach the highest resolution we can get with current technology. And I think there is a new mission that is going to go up. It's called Stage 3. It's not going to be just the cosmic microwave, but it will test other properties of the radiation. For instance, the radiation can have different polarization. And then the Planck satellite were not able to detect accurately the polarization. But with that, we'll see the polarization and we'll understand whether there are gravitational waves that come even earlier from that surface over there. So this is something which is exciting.
Will it have any implications on holography, that results which will come?
So there will be new results coming in the next 5 to 10 years.
Sir, in certain quantum theories of gravity, it states that there is a force-carrying particle for gravity as well, the graviton. But if gravity is so much weaker than the other forces, how do you design experiments to try and find such undetectable particles like that?
Yeah, that's a good question. It's not easy to design experiments because precisely for the reason you mentioned, so gravity is very weak. Or in other words, you want a huge amount of energy to put in to be able to create a graviton. I don't think anyone in the scientific community doubts the existence of a graviton, but actually seeing it, observe it explicitly a graviton, that's something which I don't think is going to happen in the near future. And this is the best collider is the cosmic collider. It's our universe here, where it says you had a huge amount of energy, it's very small space. And then it's the consequences for that we see today, as I was just describing. But directly finding the graviton, I don't think there can be an experiment that we can design here on Earth that would help with this.
Why virtual particles are created and annihilated in vacuum?
Say it again.
Why virtual particles are created and annihilate each other in vacuum?
Well, I think for all particles have antiparticles. I think for all matter there is an anti.
Why it's created in vacuum? If we see the vacuum, it has created an antiparticle and particles at the same time and annihilate each other.
So the vacuum is, even the words suggest something empty, but in quantum theory, the vacuum is nothing but empty. It's because I described earlier that when I discussed quantum mechanics, that we cannot know at the same time the position and velocity of an object. This is called the uncertainty principle. And similarly, there is an uncertainty in energy. So for very short time, there can exist energy fluctuations that generate this particle and antiparticle, and then this annihilate again. So this happens all the time. So the vacuum, the actual vacuum, is a very complicated place, and it's also very complicated to understand what is the vacuum structure of the theories I have been describing, even for theories that we understand very well, like electromagnetism or the nuclear forces. Like for the strong force, the one with the quarks and the gluons, it is still an unsolved problem to understand exactly the vacuum structure, why the gluons cannot liberate themselves.
It seems there are no more questions, so we should thank Kostas again for the wonderful colloquium.
Thank you.